No.
请品出二口。
All right. Good morning to everyone. Your quiz, we set to release it. I mean, the result of the quiz one, we set to release it on next Wednesday. And 2 more weeks, week 7, you're gonna have a second quiz. Okay, it will be on chapter 3 and 4. Okay, so hopefully we will finish chapter 4 by next week. Okay, so 2 weeks for chapter 4. Then week 7, you will have a quiz 2. Then you will have a midterm at week 9. Okay, so please arrange your time for revision. Okay, so if you have any problem or question you have when you do exercises or doing revisions, please feel free to email or message me or make an appointment with me for the office hour. Okay. So yeah, so last week we almost finished chapter 3, but this last section here we won't cover it. I think it won't be perfect, but the last section for chapter 3 is about differentiating the hyperbolic function. Okay, but as you can see here, we define the hyperbolic function using exponential function. But we already learned how to differentiate exponential function. Okay, so these are just linear combination of exponential function. Okay, so far, so good. Any question for this part? So we'll skip this 3.11. Okay. But based on what we have learned in this class, you should be able to differentiate hyperbolic function using the first two definitions. Right. So first two definitions are just a linear combination of exponential function. Okay. So okay, maybe let's ask you what's the derivative of exponential function e to the x? 加它，是加它。Yeah, okay. When you differentiate e to the x, what do you get? Hmm? 1? Yeah. Differentiating not ln x, or it's e to the x. Yeah. Yes, just ex itself. If you're gonna differentiate sine x, for example, you're gonna differentiate this linear combination here. But then we know that derivative is linear, so we can just derivative on ex and also do on e to the x. So if you differentiate EX, you just get EX. How about differentiating e to the minus x? If you differentiate e to the minus x, what do you get? Minus e to the minus x. Okay. So what rule you use? What rule you use? Chain rule. Good. So basically you use chain rule here. What do you need to set for chain rule? Okay, you just set your y equals to e to the u and then u equals to minus. Make sense? Question? Okay, so maybe you can write more y prime or dy du is e to the u because Jiang can say you differentiate e to the x with respect to x, you will get x, and you differentiate u with respect to x, you get minus. Okay, so altogether you get half of dx plus e to the x. That's it. Okay, so the result of differentiating is you make the minus sign in the middle become a plus. Question, Felicia? Margaret or Felicia? Felicia, okay, Felicia. No question? Okay. 3-1. Okay, so which part you confused? Why become -1? You mean this one? -1, this one. -1. So this is the function I differentiate here. So u equals to minus x, or we could write EUX equals to minus x. Okay, so if you differentiate u with respect to x, what do you get? -1? Yeah, this is how I get it. Okay, yes, exactly. Okay, other question? Okay, so we'll skip this part here. I don't think it will be in the exam, but it's a good exercise to see, to apply whatever we have learned. Okay, so we'll go to the next section. It's about the application of derivative. Okay, so in this section here, what we're gonna see more was the behavior of a curve. So we'll be discuss the behavior of a curve. So maybe just quickly give you an overview of this chapter here, so that you know what's going to expect later. And so let's say um, maybe let's find those. All right, so let's see this graph here. This function. And let's say let's do formulas. Okay. So the idea here was we're going to use the derivative to help us to dictate what's the shape of this graph is. Okay, what's the shape? So yeah, what's the shape? So there are a few ways to understand derivative, right? So one way is using the tangent. Okay, so maybe you could draw a few tangent or curve. So meaning you compute derivative at everywhere and then find the equation of tangent, right? This is the question that we keep seeing in the previous section. Okay, something like that. and few tangent that I need to do. And so maybe here I put them so that we know they we are coming. So do you believe that if I remove these orange curve, I can still recover my orange curve just using these blue straight lines? Do you believe? You believe or not? You believe? I gonna erase now. So let's erase it. Can you see the shape of the curve from this tangent line? Okay. So basically, you could just join these point based on the tangent line. And make sure you touch at one point. Then you can recover what we had just. Okay. So basically, these derivative of this function, right? If function is differentiable, then really you can recover the original curve using these tangent line built up by your derivative actually. Okay. So there are some notable phenomenon here. Again, notable lines here. Can you see any very some special line within this straight line here? Did you see any special line here? Special. Yeah, I need to try and observe it. You see any special line? There's some almost straight, I mean almost vertical line, but there are certainly some horizontal line. But do you still remember what the gradient of a horizontal line is? Zero. Okay, zero. Okay, so these horizontal lines sort of give you some idea. So what's the idea here? They're kind of a peak. They're kind of a peak. Okay, either they are the peak or either they are the crest. Crest, right? The bottom. Okay, or sometimes we call the maximum and the minimum. Okay, but how many maximum are here? Can you see? How many maximum? Kind of three, right? Okay, so one, this is two, this is three. Okay, they are maximum around somewhere. Okay, how about minimum? How many minimum? How many crests? Also three. Okay, so okay, out of these three maximum, right? Which one is the largest? I label already. So which one is the largest based on this three? Third one, okay. So actually, this is what we call the absolute maximum or absolute maximum. Okay, but how about the other maxima? How do we address them? Okay, so we could address them as a local maximum. Okay, local maxima here. So local maxima just means that do you guys know about the geography in Malaysia? So do you know where are you stay at now? Where? Okay, luckily you don't tell me Kuala Lumpur. Because this is the most mistake to make my patient also. They thought every part in the Selangor is the Kuala Lumpur. Okay. But more details Sepang. Okay. So local maxima could mean that maybe you are the top in Sepang, but you are not the top in Selangor. It's not the top in the state. So absolute maxima will be the top of the top. And you compare to everyone else, you are the top one. Okay, but local maxima is as long as everyone, there's someone, I mean, not there's someone, there's some neighborhood, okay, around you, you are the top. That's fine. Okay. Obviously, you don't want to include neighborhood like this. Okay, you don't want to include a neighborhood like this because there's another top than first top. But as long as you can find some small neighborhood around, okay, to be a top, then you are a local maximum. Okay. So I might not sing well in Sepang. Might not sing well in Selangor, but maybe I sing well in my bathroom. Okay, no. Does it make sense? There's no one to compare already. Okay, so yeah. Okay, so similarly, we have the idea of local and absolute in the minimum case. Okay, so if you can see here, the first minimum here will be the absolute minimum, and then the other will be the local. So far, so good. Okay, local and absolute. Any question? No? Okay, so let's go to the precise definition here. So let's look at the absolute one. So absolute is easy to check. If you want to say that FC is the absolute maximum value of F on your domain, then you just need to make sure that this number is greater than or equal to all the other Fx. Okay, similarly for absolute minimum, you need to check that your FC is less than or equal to every Fx. Okay, everyone. So if you are either absolute maximum value or absolute minimum value, we will call it a absolute extreme value. So extreme value. So they are the extreme. Okay, either to the top, either to the bottom. How about local maximum? So the same equality is checked for local maximum, FC greater or equal to Fx, but you only check for S that's near to C. Is enough. Okay, the some neighborhood is enough. Okay, no matter how small it is, as long as it is small enough. So the near here could mean the X is coming from the left and right. Okay, left and right. Okay, or in other words, this X will contain some open interval around C. Okay, so X is inside the open interval. Okay, so similarly for local minimum, okay, as long as you are comparatively small with the surrounding. And if you are either local maximum or local minimum, you are a local extreme value. Okay, local extreme value. All right. All right. Let's look at this question here. Find the absolute extreme values and the local extreme value of the function. If you look at this function, right? This function is kind of piecewise, and then obviously it's not continuous. Why is it not continuous? I'm pretty sure. Okay, so there's a gap. So after you learn limit, can you phrase in limit? Yeah, limit. Like the last chapter, we learn limit. So how do you explain if something is not continuous? Okay, so the limit doesn't exist, you can check. Okay, if it exists, you should check that whether the f take value as the limit or not. Okay, three things to check. But the result is you will see a gap. Okay, so layman term is you see a gap. But if you learn mathematics, you can use the limit term. Okay, check the limit existence. Okay, so but it doesn't affect whether we can find extreme values or not. Okay, because we are just care about the how big or how small the value of f is. Okay, so which one is the absolute extreme value? What do you think? Where is the most peak? Which one? R. Okay, so it's not R, it's FR, right? Okay, we want to look for the values. Okay, absolute extreme values. Okay, you need to apply F to R because R is just some number on the X. Okay, it's not meaningful. But FR, okay, there's some other values to attach. Okay, so is this the highest? So no one is everyone else is lower than it. How about absolute? Sorry, this one is absolute maximum, right? Okay, do you have some absolute minimum? FA, good. Okay, so if you look at FA, anything above FA, so everything else is above it. So absolute minimum value is F. Okay, so altogether, you have absolute extreme value being FRN. Okay. Any local extreme value? So maybe let's look for local maximum first. Any local maximum? Any local maximum? One try. Any local maximum? Margaret? Is Margaret here or not? Margaret? Margaret here. Okay. Try local maximum. Let's call a number and then we can check together whether it's a local maximum. F S R N F R N S are this guy. This guy. Okay. So let's check these two. So FR here. So can you find a neighborhood? I guess such that everything around this neighborhood take values below FR? Can or not? Can or not? So if you take any neighborhood, small neighborhood around R, can you find any other value other than FR smaller than it? Correct? Correct. Okay, so this is a local value again. How about X? How about S? So if you take a small neighborhood around, what do you see? Everything else is greater than it. Okay, so it shouldn't be a maximum. Yeah, we want maximum. We not just local extreme values. Yeah. Not just any local extreme value. Let's look for local maximum first. So any other? Is that all? Sorry? Someone say something here? No? I hear something wrong. From where? Did you say something? FB? Okay, let's try FB. So if you look at FB, can you find small enough open neighborhood such that all the other values it takes other than B is less than FB? Yes? Yes, right. So if you draw this region out, so you can see that other than B, anything beside B have value less than B. Okay, this is the top among all the value. So FB is one of them. FC works or not? Does FC work? So if you go to FC here, right? If you fix a small neighborhood, got points larger than FC, got values that evaluate larger than FC. Is there any? Not right. Anything on the left of C will evaluate to value greater than FC. Does it make sense? Okay. In that case, you will go to higher people, right? So maybe can I go somewhere left to FC here? Is this a local maximum? So let's draw this with purple one. So if the purple is the purple one local maximum? Yes. So if I make a neighborhood around this purple point here, any point that has having larger value than purple point or not? Got right? Anything that on the, let's say we call this a T, any point on the right of the T will evaluate to something greater than FT. Can or not? So you cannot really pick any points from this line here because this line is forever going up. Okay or not? Okay. Yeah, so basically these are the only two local maxima. How about local minima? Here we go the other direction. We find the bottom one, bottom guy. So what's the local minima here? We try someone else. Maybe with some Chen family here. There's a lot of Chen in our class. Chen, a lot of Chen in our class. Chen Yinan is here now. Where's Yinan? Okay, I try. Can you give some local minimum to check? Yeah, local minimum. FD, yeah. FD. Okay, FD. You have other answer? FA, yeah. Okay, FA. Any more? FS. Huh? FS? That's it? That's it? Okay, that's it. Okay, cool. Wait, let me zoom something. Okay, so, well, so let's check on FD first. Okay, let's check on FD first. So, if you go around FD, then you make a neighborhood around D. Let's check all the value on these open interval. So you can check that to the right of D and to the left of D, their value are both greater than FD. Okay, so it is indeed a local value. But how about S and A? S and A. If you make a neighborhood around it, right, you can see that the function actually not defined on the either on the left hand side of the A or on the right hand side of X. Okay, although we know that for everything away from A is evaluate to value greater than FA, or everything to the left of X evaluate to a value greater than X, but we won't call this a local minimum. Okay, this is a definition of convention. Okay, so I want you to remember this. So I want you to remember this: a local maximum or minimum cannot occur at an endpoint. Endpoint. Okay. Or to be precise, this is an endpoint of interval that function defined. That a function defined. Okay, why? Because when we say near, when we say X is near C, we mean that we mean that so when we say that it is true, okay, so when we say that it is true near C, something is true. We say that something is true near C, we mean that it is true on some open interval containing C. Okay, does it make sense? Okay, so whenever we want to discuss local maximum or minimum, we really need points from left and right. Okay, not just from left or not just from right. Okay, so by definition, this endpoint we won't categorize it in any local extreme values. Okay, does it make sense? Okay, so there's only really one local minimum here, FD. Okay, I got a question. Okay, so this one also contribute to that every time when we check max extreme value, we need to make sure we check the endpoint. And because these are the point we could miss out. Okay. But it's totally fine for absolute extreme values. These could happen at the endpoint. This could happen. For example, the absolute minimum value happens at the endpoint. Question? Any question? Okay, so there's something to remember here. Okay. Should we do this one? I think this one I just left as exercise. And try and do it. Should we do exercise or you want to do it now? You want to do it yourself? Are you confident? Or you want to do? Yeah. Maybe I ask for a vote. You want to do here? Or you want to do yourself? Okay, do here, you can raise out your hand. You want to do yourself? No one raise off. Okay, so I just left with homework now, so you can check the solution later. Okay, so next, extreme value theorem. So if f is continuous on a closed interval, then f will attain both absolute maximum value and absolute minimum value there. Okay. So it means that if at every point, okay, the limit exists and you can do the substitution property, okay, on a closed interval AB here. So this closed interval is quite important. Okay. Then f will attain both an absolute maximum or absolute minimum. Okay, so it means that you must have absolute maximum minimum. So can you imagine if this interval is not closed, right? What could happen? It could happen that your absolute maximum just happen at the bound at the endpoints here. Okay, you might accidentally throw your absolute maximum or minimum away. Okay, if it is defined on the open interval. Okay, does it make sense? Okay, yeah, it could be the case that the FA and FB doesn't exist, then you have problem. Okay, so it must be closer. So it must be on a close interval here. Okay, very important. So how do we find this? So next, we will introduce another piece of idea here called the stationary point. Okay, so what stationary is? Junjie here, no Junjie. You know what's a stationary? Stationary means? What is it? 文具. Oh, okay. As an English word, do you know what it means? Okay, Chinese is what? 住 is what? What 住? What kind of 住? 住宅的住. Oh, I see, I see. I forgot how to write. Okay, never mind. Stationary is 住, okay. How about the others? From others, maybe purity. Do you know what stationary means? English, not mathematics. English. Not moving, good. Not moving. Okay. Chinese Zhu also not moving, right? You stop there. Okay, not moving. Okay, the point here is not moving. So let's see what point is not moving here. So we define a point as not moving if the derivative is 0. True or not? Huh? When derivative is 0, it's not moving. Because last time we said that we could understand the derivative as a velocity as well. Okay, so when the velocity is 0, are you moving or not? Not moving. Okay, so this is a stationary point. Okay, so let's find stationary point first, and then we will see how we're going to use this stationary point idea. Okay, so I guess 4.3 is pretty straightforward, right? So let's test whether you can differentiate or not. So let's see. So f prime x equals 0. Okay, so we're going to find all the stationary points that make your derivative 0. Okay, so 6x squared minus 6x 0. And then this is just means that 6x times x minus 1 is 0. Okay, so you will take x equals 0 or x equals to 1. Okay, so these are the x value. So how to find the f value for them? So you just substitute what is f0 and what is f1. Okay, so f1 is 2 minus 3 plus 2, which is 1. So you said that the stationary points are 0, 2, and 1. Okay, so these are the two stationary points. Okay, so far I think quite straightforward. Next one is called the singular point. Okay, so if C is on the interior of the domain such that f prime C does not exist, we could call that CFC is a singular point of the graph of f. Okay, this is a singular point. So what does it mean by interior here? So if you have a domain, again, that has the so let's say the interior of the open interval. Okay, just now we said that AB is the endpoint. So anything beyond AB we call it, sorry, anything except A and B we'll call it as the interior of AB. Okay, does it make sense? Like anything inside, okay, not the boundary. So this is worse. Okay, this singular point is worse than the stationary point. Okay, the singular point here meaning f prime c doesn't exist. What does it mean by f prime c doesn't exist? So the derivative doesn't exist. So the limit of the secant around the c doesn't exist. Okay. Yeah, so let's see where does this singular point of function y exist. So maybe let's compute what is dy dx first. So maybe rewrite this form in a nicer form to see y equals to x to the 2 over 3. Again, then you differentiate this. You're using the power rule. You will get 2 over 3 over 2 over 3 minus 1. What do you get? Minus 1/3, which is a cube 1 over cube root x. Okay. So if you look at this formula here, where does this function undefined? X equals to 0. Okay, so note that we have this and dy dx doesn't exist at x equals to 0. So the singular point is 0 and y evaluated at 0. What you get is actually the origin. It's a singular point of the function y equals to. Okay. So can you imagine what happens at this point? Can you imagine? So the limit from both sides is different, but this is the limit of a secant, and so you might expect some parts, maybe types. Okay, so let's draw this. How about draw this? Let's draw this. Cube root. Okay, so you can see that this is like a V shape. Okay, but if you can see that the V from both sides is like having the secant going to the vertical line. But what's the derivative of a vertical line? Is infinity. Okay, so the derivative will should to infinity, so it doesn't exist. So this is a term that you can. It's not differential. Okay, so there are two ideas here: stationary points and singular point. Okay, these two ideas you should keep in your mind. We're gonna use it now. Okay, apart from these 2 points, there's another point called a critical point. So what's a critical point here? So these are the points as long as f prime c is 0 or it doesn't exist. So meaning what? Critical point include stationary points and singular points. Okay, so these are the critical points. So what does critical means? Madia, what's a critical means?
Critical,
Yes.
like changing,
Changing.
like most some ways and the numbers.
I mean English, just English.
Critical,
Yes.
critical run, I don't know.
You don't know? How do you use critical?
I don't know how to say, but critical.
I mean, how do you use? How do you use it?
Like mass,
No, in English.
critical, like very strong punching.
Strong punch. Wow.
In games, like
Oh, you play games. Oh, critical. Ding, like that. Push. Critical. Okay. Okay. So that's how you see critical. Can someone make the English sentence using critical? Uh, who else? Is it Daniel here or not? Daniel. Where's Daniel? Okay. Can you make an English sentence of critical? English sentence. How do you use critical? Critical. Any idea? Critical thinking. Yeah, sure. Good. So what's critical? Huh? What? Yeah, examples of a sentence, making sentence. Yeah. What is critical? What can be critical? Situation could be critical. So it's good or bad? Bad. Mostly bad. Mostly bad. So critical, there are few meanings. It's like a very important thing. Okay, or it's a very in Chinese maybe we say 关键, right? In Chinese. Important. Okay, 关键. Okay. So these are the points that are very important. Okay, we call it critical. Okay, so what are these points? These are the stationary points and singular points. These are very important. Although you might think that the point is not moving, or the derivatives doesn't exist, but these are very important points. So important for what? So this is the Fermat theorem here. He says that if C is a local extreme value, then and an f prime C exists, then the f prime C must be 0. Actually, this theorem is not good enough. What do I mean by not good enough? Okay. So for example, usually what we want to find is a local extreme value. If this theorem says that if f prime c equals 0, it must be a local extrema, then that is really good. There's only one thing I need to check. But this theorem works the other way around. It just says that to be a local extreme value, you must at least get the zero derivative. It doesn't say that every point that have a zero derivative is a local extreme value. No, this direction. And you cannot find this direction is true also. So we need to do a little bit more work. So first we need to check that the derivative of c is 0 if f prime c exists. Then we want to check whether it is a local extreme value or not. So this is a point of Fermat's theorem. And more importantly from this critical point theorem is, if FC is a string value theorem, then C must be a critical number. So not that there's no absolute or neither absolute or local that put on this theorem here. So meaning that whatever string value, whatever critical number you found later, it could be a local maximum or it could be a absolute maximum. You still need to compare yourself. You still need to compare yourself. So what's the strategy here? The strategy here is, let's restrict to the case that we have a domain that's coming from the closed interval, because using the extreme value theorem we had just now, if my f is continuous on this closed interval, you could always find the extreme values. But how do we find it? So how do we find it? By using the critical point method. Is you need to find the point that have derivative 0. You need to find the point that have derivative 0, and then among these critical number, the largest value we will call it absolute maximum value. The smallest one we will call it an absolute minimum value. Make sense or not? Following, yeah. Let's do examples to make sure we are on the same page. So let's write down the full logic we are using here for this question. So the question says find the absolute maximum and absolute minimum value of the function s cubed minus 3x squared plus 1 on this closed interval. So do you think you can find it or not before finding it? Do you think this will be a success task? So if it is success task, do you have a theorem to support you? So we're gonna use extreme value theorem. By extreme value theorem, so since my f is continuous on closed interval, do you know how to show continuity on a closed interval, Felicia? Do you know how to show? Yeah, do you know how to see this f is continuous on this closed interval? This f is what kind of function? Polynomial, right? We know that polynomial is always continuous on the domain it defined. So then so there exists absolute minimum and absolute minimum by a string value theorem. Since we have continuous here, then f attains both a maximum, both absolute maximum value and absolute minimum value. There's really only one, correct or not? There's only one top guy. this one top guy here. Maybe this absolute maximum value could happen at different places, but there's really only one y value that's the most top. Okay, does it make sense? Okay, so it could happen that like you attain this maximum value multiple of times, right? Okay, but there's really only one absolute maximum can do it. Okay, but now the problem is how to find it. Okay, how to find it. So by the critical point theorem says what? If you want to look for the upstream value theorem, it must at least satisfy the zero derivative property. Okay, it must be having a zero derivative property if your f is differentiable. But if this is this f differentiable or not? This is a very nice polynomial function. Okay, so it is differentiable. Okay, so let's find the critical point now. Okay. Let's see if we have any critical point. So let's search for the point. So let's search for critical point. So to search for critical point, you just set f prime x equal to 0. But this means that 3x squared minus 6x is equal to 0. But this means that 3x times x minus 6 is equal to 0. No, it is 2. Okay, correct. Okay. Yeah, but this just means that x is 0 or either 0 or 2. Okay, so these are the two critical points here. Do you know it is maximum or minimum now? You know or don't know? So what we should do here, we should evaluate the value to compare. Where we should evaluate the value to compare. So check. So what is F0? Okay, so also what is F2? So what is F0 here? It is 1, 0 minus 0 plus 1, which is 1. How about F2? Minus 3, okay? 8 minus 12 plus 1, which is minus 3. Good. Okay. So is it done? So can you say that the absolute maximum is F0, and then absolute minimum is F2? Are we done like this? Okay, maybe we can do a check. We can draw a quick sketch of graph x cubed minus 3x squared. X cubed minus 3x squared plus 1. Then let's look at this graph now. Okay, so our region is restricted to where? Minus 2 to 4. So how about I bring this minus half to 4. Okay, we will keep to 4. Wow, 4 is so high. It's damn high. Seems asymptote is approaching. Okay, so pretty large. Well, wait. So let's bring this image over here. Okay, let's compare our answer. So just now we say that absolute maximum is 0. So where's our region? Let's fix our region first. So minus half to 4 here. Okay, this is minus half. This is 4. And then we say that F0 is the top guy, and then F2, so minimum, very low already. Okay, let's draw it. So is it true? Is it true for this sketching here, your absolute maximum and minimum? True? True. There's someone be higher than F0. What's wrong here? What's wrong here? Okay, so this means that this maximum actually occur at the endpoint. Okay, so you need to check your endpoint as well. Okay, so if you look back to this method, right, you not only need to check the critical numbers, you also need to check the endpoint. Okay, so you need to compare, okay, with the endpoint values. So checking these two and checking the values of f at the endpoint. Okay, it's very important. This is the part that the student always forgot. They just check stationary point, or they just here check a singular point, and then finish. Okay, but you need to check the endpoint because it could happen that the maximum happen at the endpoint. Okay. So at endpoint, what do you need to check? You need to check f half and f4. Okay, f half and f4 in our case. Then f minus half is just 1 over 8. And then f4 is actually 70. Okay, 70. So that means that if I make this to 17, I should see the intersection. The intersection is here. And then minus 2 we also can see. So we need at least this big to see the graph that we plot. Okay. So here, let's export it again. Copy, paste here. Okay, so this is the graph that we like actually. Okay, so if I zoom it a little bit greater, so 17 is somewhere here. Okay, so just now what we found was f0 and then f2 and then f minus half. Minimum. So let's see, minimum correct or not? So your half, I think, is around, where is our half? Minus 1 over 8. It's 1 over 8. Our half is 1 over 8 minus half, so it's around 2. So the minimum is the f2. Okay. Okay, any questions so far? Question? And so what can you see from the lesson of from here? Because at the boundary, right, it is still continue increasing. So you cannot measure that this boundary point have a derivative of 0. Cannot. Okay. Does it make sense? Okay. So when you have derivative 0, what happens? Can you observe something? What happened when you have derivative 0? What happened to the derivative at the side of this stationary point? It is actually slowing in, increasing, and then stop, and then increase in the other direction. So positive, decreasing, positive, until you get 0, and then you increase with your negative. So you slowly tilt to the other direction. So that's why you have this kind of a turning point. Okay. So let me ask you a side question before we take a break here. So let me ask you a side question. So this maximum point, minimum point, we call it a stationary point, right? What do you think? Which one is more stationary than the other? Maximum or minimum? Huh? Which one is more stationary than the other? Maximum or minimum? What do you think? You get my answer. So which one is more? 哪一个比较稳啊 in Chinese? Which one is more stable? Maximum or minimum? So maximum is like this, right? Minimum is like this. Which one is more stable?
Stable.
Yeah, more stationary. Huh? Which one? This which one? Left or right? Right. Okay. So you could think of like if I perturb a bit, if I push this ball a bit, then if you are on the maximum, you will quickly fall down. But if you're at the minimum, I push you out a bit, you will come back to the minimum. Okay, so stay low, stay humble. Ah, okay. Okay, so let's break until 11 o'clock. Yeah, yeah, yeah.
So, in the exam,
Mm.
they only write the endpoints as the absolute maximum, not write the other points. So this was important.
Oh, you mean? Oh, depends. Depends. They are asking for the point of value. So if they are asking for value, then it's just the values. I think did we define absolute value points? Let me see. Yeah, so far I think we just define for values. Values. Yeah, so we just care for values. Because like what I said just now, right? This absolute maximum value could happen at various points. So we just want to see the greatest value that this function achieves. Yeah. Okay, let's take attendance for those right here first. 西河和田，OK，瑞阳，hello，
你发给我了，听什么？诶，怎么没有收到？有吗？没有诶，你看没有发出来，可能他没有发出来。
你是运动习惯还是什么签东西？
哎呀，钱
是疫苗签还是
硬要钱。
？OK，
有发没放？怎么没有收到？
哎，你现在是说 OK？你是
带
来
然后
戴立文
对，
？OK，
不是，哎，零
来了。拼 one side 还是 double side？
万载，
都一模一样。现在网就中间了，
现在四楼出来那个地方左边会有一个 printing area，然后在左边那
哎，
3号机，陈若石、施曼、易南、玉涛、陈玉涛、易哲、瑞阳、邓瑞阳、泽汉、嘉来、嘉诚、嘉怡、OK，齐军、易清、俊逸、俊逸狗 right，OK，相思、易林、冰珍、江南、浩云，OK，浩云，OK，文琪、安祥、俊杰、新阳、万达、新月、玉恒，got right，一田、冰城，杨冰城，浩然，Desmond，Tommy，琼一，英杰，Go Go Pagani， Islamova not here, right? Can cancel this name. After Ariando, Isham, Daniel at the back. Is it Daniel? Hashim, Hashim here. Hashim, not here. Fadia, yeah, right. Aaron, yeah. Brandon, Felicia, yeah. Gunakanti, 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 not here. Hashim, not here. Gunakanti, Hashim, not here. Margaret, here. Hassan, Hassan Khalid, not here. Wow. Starting to disappear since last week. Javed. Yep. Gabriel. Jeffrey. Yes. Purity. Yep. Some fun. He Yating. Yeah. You was not here last week? What happened? Oh, why? Holiday. Oh, holiday. Okay. Hong Liang. Okay. Right. Continue. Okay, let's continue. Okay, let's do 4.6 on your own first. Then we will discuss. So, yes. I should duplicate this better. Okay, let's do 4.6. I'll let you try first. See what you
以前過往呢啲叫做平時。
okay.
HM 嗰啲。呢個你講呢度點？叫咩話？
这个不，这个是OK。所以的
60個人，
好，希望可以来领。新啊，一般。
也沒有這樣多啊。
哦，
應該係少
1/3，
3分之一樣三分之一。
很多。OK， 好。Okay, please take this chance to try. This is where you stay here. Don't make mistake in your quiz. They will be painful. Okay, so you should try here. You can discuss. I'll give you 1 more minute. All right, just now, someone asked me, should I write point or just write value is enough? So it depends on what this question asks you. So this question asks you about maximum values. Okay, so you just find the values is enough. Okay, yeah. Because you should keep in your mind, like what I said just now. This value could be attained several times. Okay, maybe got different x that have the same value. Yeah. Okay, so if you need to spell out all the points, then enumerate them. Otherwise, mostly I think question will just ask you about values. So please be sensitive about the question. All right. So what's the first thing you do here? Okay, so immediately observe that this is the polynomial function is continuous everywhere where it defines. So you must be able to find absolute maximum or minimum values here by S-string value theorem. Although in the exam, maybe we won't require you to write down all these logical steps, but I think this logical step will help you to think about the question better. Yeah. So for this class, maybe it's not very important for you to argue why they exist. As long as you found them, that it should be good enough. Okay, but at least you have an idea in your mind that continuous function on the closed interval, you should be able to find these absolute maximum or absolute minimum value. So how to find them? You need to resort to the critical points method. Let me do a result to the critical points method here. Okay. Right. So what's the first thing you do? So you check when is it getting f prime x equals 0. And because if it is a polynomial, it's always differentiable as well. So go and find where this derivative achieves 0. So you get 3x squared. Hey, sorry, this is we did it. No wonder feel very familiar. Okay, how about this power function here? Does this power function continuous or not? Okay, it should be continuous on this region, -1 to 2 here. Okay, so similar idea. So let's check when is 0. So this is 0 when 2 over 3 of square root cube root x 0.
There's not.
There's no point such that. Yeah, so but unfortunately you can't get any very useful thing from here. So what else you need to go and find? Where else you need to go and find? Okay, so you fail the stationary point. So you still got two things to check. The critical point, sorry, the what do we call that? Singular point, and then the boundary, the end point. Okay, there are two more things to check here. Okay. Previous case, there's no singular point because your f prime is very nice. But now there's a singular point here. Not that. F prime 0 does not exist. Okay. If you notice, this is what we have did just now, right? From a previous question. Actually, example what? Let me spell that out. So this is the example 4.4 from 4.4. Okay, so from example 4.4. Then we know that it doesn't exist. So x equals 0 is one point we need to check. So as 0, 0 is a singular point. Okay, so we need to consider this. Let's check all of them, compare them, since we know the endpoints already. So we need to compare what is f0, what is f minus 1, and f2. Upon checking, check the value of singular with value of endpoint. Okay, so these are the things we need to check. So f0 is just 0, we have computed. How about minus 1? So minus 1 to the 2 over 3, you just get 1. Okay. 2 to the 2 over 3, I don't think you can evaluate further. It's just a cube root 4. Okay, so which one is larger? Which one is smaller? Last one is the largest one. So the absolute maximum value. So I stress this is a value. So this is f2. And the absolute minimum value is what? F2. Okay, good. Oh, good. Okay.
I
So
don't understand the
yes.
singular point.
Huh?
Singular point.
You can't understand. What do you mean by you can't understand?
Why we like define that 0, 0 is a singular point? Like,
Because singular point, it just says that the derivative at the x equals 0 doesn't exist. That's it.
if it doesn't exist, so
Mm.
any function is single point 0, 0.
No, right? Because wait, let me see. The point, singular point include the whole point. Yeah, correct. Okay. So what do you mean? This singular point must be a point from the graph of f.
But if we don't
Yep.
have graph,
If you don't have graph, no, it must be a point on the graph of f. Do you mean that that point doesn't exist in the graph of f?
it, I know that
Yeah.
but
Mm-hmm.
how we
Mm.
know that
Mm.
like without any proof right now.
No, the proof is you need to check what's the derivative at that point.
This does not exist.
It doesn't exist, then this is what we call a singular point. Does it make sense? So every point you can find the derivative, right? Supposedly you can find. So if you cannot find, then it is a singular point. Does it make sense? So we use derivative to check. So if the derivative is 0, we will call it a stationary point. If the derivative is doesn't exist, we call it a singular point. If the derivative exists, is non-zero, what do we call it? Just some normal point. Okay. Yeah, it's just some normal point. Okay, but why we categorize these 2 points, these 2 kinds of points? Because these 2 points will contribute the maximum minimum. Okay, because if you imagine this derivative is non-zero, either is increasing or decreasing, meaning nearby it, there will be some point lower than it or higher than it. So it doesn't fall into maximum or minimum category, even for the local sense. Because there will be someone higher than you, there will be someone lower than you. You are in the middle of increasing or decreasing. Does it make sense or not? This is the point that you want to buy stock. Anyone understand what I'm saying? Do you guys know about stock? Stock. STOCK. 股票 is stock. Okay. So this is the point you want to buy stock. Either if it's increasing, you want to buy, decreasing, you don't want to buy. Okay, if you want to buy at the maximum point, then you are pretty much GG. GG, right? Because if you buy at the maximum point, it's gonna go down soon. So minimum point maybe is the one that you want to buy because it's going to go up soon. Yeah. This is how you apply these calculus. If calculus is any useful. Okay. Okay, so this is for this question. 4.7 we will skip. For less for you for homework. This is very similar. Okay, let's go to the next theorem. It's about the derivative mean value theorem. Okay, so mean value theorem, you should think of it like the middle value, right? The middle value. So how do we get some middle value here? So first, we start with Rolle's theorem. So Rolle's is the name of a mathematician. So what Rolle says that is, if f is continuous on a closed interval AB and differentiable on its interior in the middle point, not counting the endpoint, and we know that the value of the endpoint are the same, then there is a C such that f prime C is 0. Okay, so this is very interesting. Why is it interesting? F prime C equals 0 meaning what? There's always a turning point. Okay, is it true or not? Okay, so if you start with 2 points with the same height, okay, and you know that you will go through some continuous path, there must be some turning point. Okay, if you say I don't want to turn, if you don't want to turn, what could happen? You just don't move. Once you move, you must turn. turn back. Okay, so the turning point is the maximum or the minimum point. This is the point that give you the zero derivative. Make sense? Okay, this must be. Okay, the idea is very clear, huh? Okay, you must turn back because you are continuous. So if you go away from your starting value, but you want to come back to the same value, you must somehow come back. Okay, you must turn back. So this will create the maximum and minimum. Okay, so the more general version on this Rolle's theorem is what we call the mean value theorem. Let's say your starting point and the ending point is a different values, but again you have the continuity and differentiability condition. Then what could happen is if you get a secant, okay, between the starting point and the ending point, there must be another tangent line that realize this derivative. Okay, does it make sense or not? Does it make sense? Okay, so this idea is the same as the Rolle's theorem. Why is the same idea? This is just a tilted version of a Rolle's theorem. So meaning, if this is true, why is this true? You can tilt this A and B to the case of Rolle's theorem, where the value of A and B is the same. Then these tangent line will become, this secant line will become horizontal. Does it make sense? Okay, so this is really a generalization of the Rolle's theorem. So if you maybe I can draw a version that can tilt so that you can see what am I talking about. How about I draw this, okay, and then this. So the idea here is if you are continuous, you can find another tangent line with the same derivative. Okay, so this is how I build it. I'm not redrawing it. I'm borrowing the same tangent line so that I can show you it is going to happen. Then I think GoodNotes have updated such that I can rotate it. Let's test out this function here. Yay, I can rotate. So if I rotate this to horizontal, this is just a Rolle's theorem. Can see? Okay, so previously it's like this, right? The endpoint has the same different value. But if I rotate it, this is just a Rolle's theorem. Okay, so it is really a generalization of Rolle's theorem. Make sense? Okay, so this is a very cool result. If you take the secant on the endpoint, then there will be another tangent line that realize this derivative. Okay, so this is the idea of turning back actually. And so if you want to come back to the other point, then you must has a turning point. Okay, so where's the mean value here? So where's the mean value here? Actually, this derivative is what we call the mean value. So this derivative is what we call the mean value of. Okay. Okay, actually, it's the derivative of the secant at the joint endpoints. So how is this useful? Yeah. So let's see. Before we check how useful is it, maybe we'll use this mean value theorem first. I think there are very few theory in this course, but perhaps this is one of the theory that you want to know. Okay, you need to know. Maybe we could test on an exam or quiz. Okay, so make sure you know the basic use of this theorem. Okay, so let's see how we're gonna use this mean value theorem. So first, let's learn how to find mean value. So what's the mean value here? Just now we say that the mean value of f is just what? The ratio, okay, the ratio of value of f at the endpoint against the difference in x. And this is the mean value of f. Mean value f is equal to this. It's defined as this. Okay, is the derivative of the secant. So what's this then? So this is 2 square root 4 minus 2 times square root 1 over 3, which is 2 over 3. So next question. Find the number c which satisfy the conclusion of the mean value theorem. That is f prime c attain the mean value of f on 1, 4. Perhaps we want to try and draw this to give us some idea what we are doing actually. So still remember the basic graph of 2 times square root x. So it's something like this, right? Okay, but we just want to chop it around 1 and 4. Okay, so when it is 1, what is the f1? f1 is 2. Okay. When it is 4, f4 is 4. 4, right? 4. The point here is you found the mean value, so meaning you found the gradient of the secant here. Okay, so this one has the gradient m equals to 2 over 3. And let's use m. So the point here is find a c. Okay, find a c such that you have the derivative the same as this 2 over 3. So let's copy, paste. So can you see where is it from this graph? So you just move around this line here. So where does it match? So maybe somewhere around here. Okay, somewhere around here. So we want to find what's this. What's the C? Okay, makes sense. Okay, but how do you find it? But this is amount to find f prime x such that it is equals to 2 over 3. Okay, but then meaning you need to find what is f prime x. So do you know how to differentiate this? So this is 2 over 1 over 2. Okay. And follow. And differentiate 2 square root x. So you bring down the half and then minus half. Minus 1. So you get minus half. And then this is what? This one cancel. So x equals to 2 over 3 to the power 2. Which is, did I make some mistake wrong?
Yeah.
Yeah, I think it's 3 over 2, right?
Yeah.
Then if it's 2 over 3, then it will be somewhere here, right? Should be wrong. Okay, obviously wrong. So you see, if you do these sketching, right, it will help you to check. So now it's 9 over 4. So this point should be 9 over 4. Okay. Yeah. So there's only one point that achieve it. Okay, but the theorem says at least one. Okay, so you found one. Yes. So 2 over 3 is the mean value of f. And c equals to 9 over 4 satisfies the conclusion of, let's abbreviate it to MVT, the mean value. Okay. So please make a good habit, okay, good habit that after all the calculation, write down the conclusion, okay, so that we can easy check what's your final answer. Otherwise, your answer is like loose inside the sea of calculation. I cannot find it. If I cannot find it, do you know what happened, Felicia? If I cannot find your answer, what happened? Huh? Yes, good. You just lose mark. So because in for example final exam, you cannot check it anymore. So if you lose mark, mean you lose mark. But people still complain, right? You know what can they do? Final exam, they're not happy about the result. You know what they do? You can appeal actually. Okay, but when you appeal, whether success or not, you must at least pay 50 ringgit for one subject. Okay. But most of the cases, they fail. I mean, cannot do much actually. Okay, so make sure you write your answer clear. Okay, write your conclusion. Okay, so that we can easily check. Okay. Next, I think this one is similar. This one we just left as homework. This one is similar. But we'll do the next one. Okay, next one is more involved. Let's do this. Use the intermediate value theorem and mean value theorem to prove that this equation has exactly one real root. So let's think about it. Okay, let's think about it. How you gonna use IVT? Okay, IVT intermediate value theorem and MVT. Okay, to prove it. Let's think for a moment first to see why these two are involved. Okay, I give you 1 minute to think about what this question wants. Then we'll see how we're gonna use the theorem that we know. How about Aaron? Aaron. Okay, Aaron. So what does this question trying to ask? What's this question trying to ask? What does it mean by exactly one real root? What does this root do? What does root mean? Root means what? What does root means? Don't know? No idea. If you no idea, then Finisha cannot do this question already because you don't understand. So who else know? Who is behind Felicia again? Huh? Hosaya? Arianto? Arianto? Oh, Hosaya. Okay, Hosaya. So what does it mean by root? Factor? Right, from factor you can get the root. So the root actually is the x that makes your make your value 0. Okay, so meaning there's a solution to this. Okay, solution to this equation here. But real roots means what? It's not a fake root. Real is just a real number root. Okay, because sometimes the root could be complex. Okay, so this is a real number root. So exactly one. You must prove that there's only one answer, one solution. Okay, so is it hard or not? But IVT, since the question already hints you, okay, maybe MAT for MAT students, we won't put the IVT and MVT. We just say that prove that this thing had one root. So you should think about what the important information you need to extract from this question. But now already hint you that you need to use IVT and MVT. So to use IVT and MVT, what do you need to have? What thing you need to have? You need to have a continuous function and also a differentiable function also. Okay, continuous on the closed interval, differentiable at the interior. But then what? Then what's the continuous function you want to have here? Is it obvious? What's the continuous function you want to try here? Is it obvious? What's the continuous function you're going to try? Is there a function you see here? Any function you see here? Any function? Is the left-hand side a function? S cubed plus x minus 1. Is it a function? Function or polynomial, right? Polynomial function. Okay, continuous or not? Continuous, right? Okay. But now you need to determine some closed interval to work. Any nice closed interval that you want to fix? Any interval that makes sense to study here? Or let's think about IVT. What does IVT do? IVT says that if you have FA, you have FB, then you could have everything in between FA and FB. Okay, good. So now what's the value you want here? If you set your, okay, so let's consider your fx. Okay, so let's say this is your function you want to consider. This is continuous and everywhere, very nice. Okay, so you want it to be 0, right? So if you're going to use intermediate value theorem to make sure that you have this 0, you need to make sure that you have f that is above 0 and below 0. So you need to find some fx such that fx is greater than 0 or less than 0. Okay, can you find these 2 points? When does this 2 point happen? When is fx greater than 0? When is fx less than 0? Do you know? When is fx greater than 0? When is fx less than 0? Any systematic way to see it? Sorry, 0 and 1. So how do you find it? Do you just test value or just test value? Okay, sure. I think test value is fine because we just need someone that gives us something positive and something negative. Okay, so let's take take s equals 0. So what do you see? F0 is actually -1. And then x equals to what? What did you say the other value? 1. 1. 1. Okay. So if 1 is f1, f1 is 1 plus 1 minus 1, which is 1. So 1 is less than 0, 1 is greater than 0. Okay, good. Okay. So also we see that, what do we see here? Fx is actually continuous on this closed interval 0, 1, and is differentiable on these open interval. Okay, so satisfying the condition for IVT and MVT. So by IVT, intermediate value theorem, what does it say? It says that there exists at least a real root, at least a real root C in 0, 1 such that FC equals to 0. It just says there's 1. Okay, but now we want to show that there's exactly 1. There's only 1. Okay, so we're going to use MVT to help us. What does the statement of MVT tell us? Okay. It says that if it is continuous, then there's some derivative that realize the secant on these two endpoints. Okay. So how about we okay, I think calculation is not enough here. Okay, so I think there's a technique you have to learn. So if you want to show something is exactly 1, how do you show something is unique in this world? I say I have a Benz or a Mercedes. Is it unique or not? I have a Mercedes car. Is it unique in this world? No. Why? How do you know it's not unique? Because you can find another Mercedes car. So if you want to show something is unique, you should say that if someone has this Mercedes car, this is the same as your Mercedes car. Correct? Okay. So the technique is if we want to show that there are two of them, I mean one of them, only one. Suppose that there's another one. We want to show that these 2 points are the same. Let's suppose they are more than one trivial. Okay, so let's call it C1, C2, such that FC1 equals to FC2, 0. Okay. Then what does it mean here? Okay. So this provides a stage for MVT because you have 2 points that give you the same value, or you can try and find what's the derivative of this secant. Okay. So then either you want to use Rolle's theorem or you want to use the more general version of MVT. Okay, actually there exists another point in between C1 and C2. Okay, this is open interval such that f prime of d is equals to 0. So if you use the MVT here, this would say that, let's say this is C1 to C2. So here is FC1, is FC2. Okay, so there's another point that have derivatives. Okay, but what happened here? Let's compute. Is this gonna happen? So note that f prime d equals 0 would mean that what is the derivative of this function? Would mean that 3x squared plus 1 equals 0. Okay, but can you find, sorry, that's d. Can you find d such that d squared equals to minus 1/3 or not? Can you find this point? No. Okay, so there's a contradiction here. But no real d such that d squared equals to minus 1. So maybe you need to go into the imaginary world to find it, the complex world. Okay, so no real d such that this is true. So MVT doesn't apply. Hence, there exists exactly once such that FC equals to 0. Okay, so actually we are using contradiction. So contradiction technique. Contradiction proof technique. Maybe you will see this in your discrete math again. Okay, so if you want to prove there's exactly one, suppose there are two, then there's some contradiction, or you show that these two are the same, then you will see that there's only one. See, that's it.
What about if it's like a parabola?
Yeah, things could change. Things could change. Parabola meaning what?
Like in a parabola, we have two roots.
Yeah. Yeah, sure.
So if it's like that,
then this proof wouldn't work for this case. Then meaning maybe in this part you are successful, you can get something out of it. You can really find what's your root, right? But in this case, there's some logic breakdown here. Where you cannot really find this thing. Yeah. If you change your function, obviously, this proof will move the other direction. It won't get the same result. Does it make sense? Yeah, it's not like whenever you apply this method will work. This method wouldn't work if you change different cases. Okay. Yeah, this is about proving.
it's like it works only for x power of 3.
Works on actually, I cannot say that this is a universal proof. It means that I'm not sure if it always work if your function is only having exactly one real root. Yeah, I cannot say for sure. Okay, so what I can say here was this is just one method to prove. One method to prove. Yeah. I cannot say for sure if as long as you have exactly one real root, then you should go along this route and then you will see something square. I mean, like, because this is a cubic, so that's why you derivative is a square, then your quadratic solution doesn't exist. But let's say your function is a power 4, then your derivative is cube, then maybe you will get different kind of contradiction there. Make sense? Yeah. Okay, so it's really depending on the real situation. But the core idea here is you suppose there are two things exist, and then from these two things, you use whatever you know, and then you get a contradiction. Then that's it. So this is the core idea. Okay, you get contradiction. This is a kind of proof technique. I think for now, I think this is the first proof that you have seen. Most of them should be calculation. I think this is the most concept part in this topic. Okay. Other than this, you will be still calculating. Just calculate. Any question? Maybe today we can stop here. Question? Got question before we finish? No questions so far? Okay. So if more question, we can left Friday, and we'll continue on Friday.
Yep. 现在还不能用单调性吗？所以说。